is the information I just pulled off of the website regarding when the final is going to be. So I hope we're all in agreement with my interpretation of that. Okay. Yeah.
It's in this room.
Yeah, as far as I know, it's always in the same room.
I haven't taken an in-person final in a while, so.
Oh, an old style throwback thing. Yes.
And there seems to be less material on this exam than previous exams, and the time is longer.
Right.
Can we expect like a shorter exam, or are you?
You can expect a shorter exam, but yeah, questions can still be challenging.
Okay.
Yeah.
All right. Just wondering.
I have two old exams I can put onto the website. I don't think
Our time is 12:145.
Yeah, that's right. So expect to finish early.
Is it here in this room? Or?
Yes, as far as I know, it's in this room. I've not gotten any other information.
If you do get other information, please like email or post that.
Oh yeah, oh sure, yeah. But I guess I'm stuck in the past. We always have the exams in the same room as the classroom. Does that happen differently, or maybe again we haven't had in-person exams for so long, but.
Calculus and chemistry, is that how it works different around?
Say again, what?
Like, like freshman calculus and chemistry is usually switch rooms.
Oh, they do? Mm-hmm. Well, they have like 300 people. Yeah, right, so they need special rooms. Yeah, okay. Any other questions about the final? All right. So, this is something that we talked about a little bit already. But we'll start out with a kind of review and expand on what we already know, talk about other polymers, and then move on to OLEDs and how what you see here factors into how those function, and it very definitely does. So as you know, most polymers are electrical insulators, and of course we rely on that. Polyethylene and polyvinyl chloride are basically, you have hot wire, it goes into a hot melt, and the wire doesn't care about how hot the melt is because copper is very insensitive to that, and it gets drawn out through the melt, extruded through a tube, and you end up with a coating. And then that wire at meters per minute goes into a chamber in which it's bombarded with X-rays or gamma rays, which cross-links the polyethylene and PVC. All right, we all know why we do that, to improve the durability of those wire coatings. Okay, so works for acetabular cups, it also works for wire. All right, so they have these very special rooms that are very hazardous to enter into because there's such a high X-ray flux, but the little wires go in and out, and that's what gives us our ability to handle electricity in these kinds of forms. So that's part and parcel of how we live these days. Some polymers having special electronic arrangements or structures are conductive, and as you know already, these are given that ability by the presence of double bonds all the way up and down the length of that polymer chain. All right, not every single pair, but in between pairs. All right, and the one example we talked about before is polyacetylene, and as a result of that type of conductivity, the conducting polymer can possess the electrical conductivity of a metal. Not depends on what metal you're talking about, but yeah, it can get to the conductivity of a metal. And then the real advantage is that the mechanical properties, especially the processability, commonly associated with conventional polymers. So again, we're all used to copper wiring. We talked about the fact that when you get on a plane, you're paying for that ton of copper wire to fly back and forth across the country with you. All right, so if you could make it out of polymers, not only would it be lighter, it would also be a heck of a lot easier to make wires out of than copper. And so, but the other side of that coin is that as everything becomes smaller, polymers are really good at getting smaller. All right, and so we'll talk more about that in a minute. But the fact that they can be processed and aligned and extruded and made into very, very small things relatively easily, they can be coated out of solution. There's a whole bunch of possibilities if we can look at making circuitry out of polymers. In some cases, though, people have called these polymers synthetic metals, which is usually something that people are trying to get funding say. But anyway, that's just a word that has been batted around resulting from these types of inherent behaviors associated with all these double bonds. All right, and so this is just showing you some of how things stack up. And so over here we have the metals that we're trying to compare to. Doped germanium, which is these semiconductors, silicon, which again can be doped. And then we have polyethylene, nylon, polystyrene. So down here, we're firmly in the range of non-conducting materials, these insulators with a certain type of conductivity range, polyethylene, nylon, polystyrene. And then semiconductors, which we all know are useful. All right, so polymer semiconductors are a thing as well. There's weight gain advantages, but of course there's so little silicon in a semiconductor, the weight's not so important. But you can make polymer semiconductors, which is certainly done. And then we think about things that are true conductors, 10 to the minus third to 10 to the sixth, these particular units. And those are shown here: polyacetylene, polyphenylene sulfide, and polyparaphenylene sulfide, and then of course polyacetylene. What's the problem with polyacetylene? Pretty pronounced problem with polyacetylene. Yeah, nobody remembers that? You take polyacetylene, you expose it to air, what happens to that polyacetylene?
It.
Kind of, it does something.
It sounds very familiar.
All right, so it bursts into flame. It sees oxygen. The oxygen goes and attacks all those double bonds and gobbles them all up, generates heat, and goes poof, the whole thing. Water doesn't help. Water also attacks those double bonds. All right, so clearly polyacetylene, even though it's the basis for what we know about conductive polymers, that's how it was first discovered, is environmentally sensitive, very sensitive. And the guys in New Zealand or Australia that discovered this, they were dealing with a vacuum, and they had specific impurities in their vacuum system, like iodine, that made all of this work. And that was used to demonstrate it, and the guy won a Nobel Prize and all that stuff. But it's not very durable or useful unless you're in outer space or something like that. And so these alternatives, these polyparaphenylene and polyparaphenylene sulfide, they have slightly different polymer groups, but they also have much greater durability. And so they don't burst into flame. And there's a whole bunch of them. You'll see some more here in a minute. And they also have different ranges in terms of their conductivity, which can turn out to be useful as well. But a lot of it has to do with capacity as well. And that's kind of where these really shine in comparison to polyacetylene, is they can conduct more current. Right, and we talked about this before. The limitation of a lot of these polymers and why we haven't replaced copper is because they can't deal with a lot of current. All right, and so getting them to increase their current carrying load is really necessary and actually very difficult at this point in time. All right, any questions about that? All right, and so conducting polymers, as you've seen, are more than just polyacetylene. We have polypyrrole, polythiopene, what's called PDOT, poly-3,4-ethylene dioxythiopene. We used to make stuff out of this in the lab. And then polyaniline. All right, and so out of these, there's a lot of different choices. You can see that they are, in some cases, putting sulfur into these groups, which is part of A, why they're more durable, and then B, why they have greater current carrying capacities because of the presence of that sulfur. So there's a lot of relatively exotic chemistry that can go into making these things. But they all had the same theme that we're used to looking at, the presence of a lot of double bonds. And sometimes those double bonds are inside rings, and sometimes they're outside the rings, but those double bonds are still necessary here in order for this process of conduction to occur. So it still involves those electron clouds, and they're still doing the handoff between their neighbors. What makes that process less efficient, or I guess more efficient or less efficient, depending on how you look at it? You guys remember? I'm asking you because it'll probably be on the exam. You remember this about, what are the limitations besides the bursting in the flame thing? You guys remember? All right, so these structures can be amorphous or crystalline, okay? And this is one of those cases where you really want crystallinity. All right, so when we take this polymer chain and it's in just an amorphous floppy case, all right, then everything's sort of loosely organized, and it's more difficult for the electrons to move down the chain because it's amorphous. Right? It doesn't really have a defined shape. We know that. If we take that same polymer structure and force it to be in a crystal against its entropic will, you force it to be in a crystal structure. Now everything's rigid, everything's defined, and so those electrons can move down these chains much more efficiently in the crystalline state than they can in the amorphous state. So, in an ideal world, what we do is just make one giant crystal of polypyrrole, and we have fantastic conductivity down the length of that crystal. But as you guys know, that is completely impossible. All right, we have full surfaces, we have intersections between these lamella as they grow and nucleate. We can't get the kind of single crystal formation we really need from these systems. All right, so within the crystal, we kind of have the ideal behavior that we want. It's between the crystals where things start to break down. Does that make sense? Make sure you're very clear on that. Any questions about that? I think that's one of the old tests that I sent you will have that as part of the answer to that test. So make sure you understand that aspect. Crystallinity is useful to us in this context. Unfortunately, it can't be controlled as well as we'd like, but it is certainly important in how these things are applied. And so that's the mechanism of conduction with these polymer chains and some of the limitations in terms of conduction. With metals, of course, we all know that we have a crystalline arrangement of cations within a cloud of electrons, or a sea of electrons, all right? And we apply a potential. That sea of electrons moves left or right, depending on how the potential drives them, all right? And so with their neighbors, that potential could just drive down that long chain of copper atoms, all right, and go wherever it is we need it to go. All right, and that's the nature of these cationic cores within a cloud of electrons. With polymers, it's not that. It's not the same thing at all. The question? These free electrons provide the necessary charge carriers for electrical conduction in metals. All right, so that's how that works. The electrons aren't really associated with the cations very tightly like they are with polymers, of course. We need the double bonds for electrons to move. Metals, we don't have double bonds because everything is loose and able to slide around very easily. And so, what we're looking at in this process is the valence electrons in normal carbon-carbon covalent bonds are tightly held and shared between the atoms. And so these are not available to act as charge carriers. So the single carbon-carbon bonds don't work for us as charge carrying capability. In contrast, the pi electrons are relatively free compared to those sigma electrons, and those pi electrons exist in double bonds. And so you guys remember that we have these chains and some double bonds. All right, and then we have the p orbitals sticking up and down, all right? And that's where the action really is with these systems, and that these electrons, let's go to that color. These electrons can exchange between the clouds, all right? And then vice versa, holes can move the other way when we apply a field, either E's or holes. Right, both of these can be used to conduct current. This is supposed to be something you've seen before. A question about what I'm drawing? So the p orbitals stick up, right? In these large dumbbell shapes above the atoms, above and below the carbons, and they're basically the empty shells into which electrons can jump and move. Okay, and when this is crystalline, everything's ordered. The distance that the electrons have to jump is the same between every carbon atom. When it's amorphous, all bets are off. And we got hopping, remember, diffusive hopping, which is nowhere near as efficient as this nice line of sight that we can get in the crystalline structures. Any questions about that? All right. So in polymers containing conjugated double bonds, i.e. the double bonds we're looking for, delocalization of those pi electrons inside of those p clouds can occur via the interaction of these neighboring pi orbitals. And so that's certainly important to us. And ideally, this delocalization can make these pi electrons freely mobile along the length of the polymer molecule. And that's what this fuzzy-looking drawing is attempting to show, and that we have these charges. They can be positive or negative, and they can move in either direction depending on whether they're holes or electrons. All right, positive bias will move electrons one way, positive bias will move the holes the other way. I know you guys have had, most of you, at least 2010, so some of these things should be familiar. All right, any questions about this so far? Conjugated polymers in their pure state are still electrical insulators. All right, so regardless of what I just said, in their pure state, there's nothing there to cause a charge imbalance. So these pi electrons and these above the carbons, there's no reason for them to move. All right, there's nothing there that causes an imbalance that drives charge up and down that chain. So they aren't naturally conductive by themselves. And so what's necessary, which is what the guys in New Zealand did, is doping. And as we'll talk about in a minute, they were, it's not very clear, but they were looking at polyacetylene, and apparently they had some iodine contamination in their chamber. They didn't even know it was there. All right, and the iodine comes in and causes these charge imbalances to occur, and they got charge carrying capability as a result of the presence of the iodine in their chamber. It was not intentional. They had other experiments like, oh, this stuff doesn't conduct worth a damn, but you put iodine in there and suddenly a current shows up. All right, and what the iodine is doing is creating charges that don't belong, and then the rest of the chain responds. And we'll talk about that in just a second. And so we need this type of conductivity and these types of doping processes to occur. I'm trying to get everything to move in the same time. All right, so one example of this is doping the same stuff, polyacetylene, with arsenic pentafluoride. Okay, and so this particular compound is the ability to accept an electron. And so what that means is it shows up and it sees those double bonds, and it's kind of like the burst into flame thing, except it's not really attacking them, it's pulling electrons out of them. All right, so you're not putting a ton of this in there. If you did, it would burst into flame, but just a little bit of doping accepts electrons that would normally be inside those polymer chains in those double bonds and creates this hole that we're looking for. All right, by causing that charge imbalance. And so I've got this little movie, which hopefully will run. Let me try to blow that up a little bit so you guys can see it easier. All right, so straighten up. Come on, fly right. Okay, so let's see if I can get it to stop at the right time. So we have, so this is kind of what's going on. Initially, you have all these double bonds, and we bring in this arsenic pentafluoride, and what it does is it abstracts an electron out of the polymer chain. All right, it leaves one behind, and in doing so, it's resulting in a net positive charge on that carbon. Now this guy, this double bond that used to be a double bond, now is a single bond, and so there's an imbalance there, and so what happens is the electrons start moving down the chain trying to find another double bond to take up residence in. And so what you see them do is scatter down the length of this chain, boom, 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 just kicking around. All right, so what I'm doing is I'm trying to show you this is to give you an idea of the fluidity of these double bonds and the electron distributions above these double bonds, okay? And this is how it can work. It just scatters down the length of the chain based on these interactions of the double bonds. The double bonds go back and forth between single bonds and being double bonds, all right? Because the only thing that makes them double bonds is the presence of those electrons. And as they move, the status of the bond changes very quickly, all right, but it does change. Does that make sense? I know we've been talking a lot about how double bonds, they never change, they're inviolate, but when you do this to them, these electronic changes can shift that back and forth very quickly between being single bonds and double bonds. All right, so that happens, and then those positive charges that are left behind are what are causing current to move. All right, as they move under the influence of some large electric field that's placed on this system. Does that make sense? All right, any questions about that? So that's how this process works. And again, it's most efficient when things are nicely crystalline.
Are there any triple bonded polymers that can be conductive, or?
Triple bonded? No. I mean, it's hard because if you have 3 bonds to a carbon, then you're not left with room for bonding to anything else. All right. Now, of course, there's graphite, which is quadruply bonded, and that is conductive. All right, but it doesn't work with this technique. It's a different technique. All right, and so doping then is a process of charge injection into conjugated polymer chains. And you cause that charge imbalance to occur, and then the applied field has something to move. All right, without the charge imbalance inside that, nothing moves no matter what a field you apply to them. And so we have a couple of different ways of doing that. The P-type, and we just saw an example of that, the arsenic. Here it says hexafluoride, before it was pentafluoride. Iodine, which is what they originally did in New Zealand, is phosphate hexafluoride, boron hexafluoride, chlorine. These are things that will accept the electrons in the system. And then you have N-type, which donate electrons, sodium, potassium, lithium, calcium, tetrabutyl ammonium dopants. All of these things can be used to put different types of charge carriers in the system, which represent imbalances, which can then be moved by an electric field. All right, and you need this, and they were lucky enough to have this when they did that original work that got them the Nobel Prize. Otherwise, they would not have gotten the Nobel Prize. All right, so we got, you remember, hopefully these are basically in the semiconductor regime, right? We have the top of the valence band and the bottom of the conduction band, and these represent transitions, all right, tunneling between those different layers that make these electronic behaviors possible. And so applications, we talked about the first one, electrostatic materials, all right? And so these, again, I said before, they don't conduct a lot of charge or a lot of current, but statics is a slow process of buildup. And so if you slowly bleed that off before it has a chance to build up, you have a cure for the static charging process. And so this is very important in a lot of applications involving semiconductor manufacturing, where this kind of thing can be a real problem. And so it can be useful there. Conducting adhesives, of course, can be handy if you want to glue two things together. EMI, or electromagnetic shielding, which of course we need for a lot of computer applications. Anesthetic clothing. Active electrodes, or electronics, diodes, and transistors. There's one example of aircraft structures, which I have not been able to find, but people say it's important. It's probably a sensing thing. One that's certainly very important is molecular electronics. All right, you guys are familiar with Moore's law? What does Moore's law state? Nobody's ever heard of it but me? Come on. Has anyone ever heard of Moore's law besides me? Yeah, one person. Okay. Anyone know what Moore's law says?
The number of transistors will double every 10 years?
Every 10 years, right. So basically the size of electronics will have every 10 years is what that boils down.
Material engineer, not electronic engineer.
What?
Material engineer, not electronic engineer.
Yeah, but I don't know. You watch PBS, you hear these kinds of things. Okay, so this is what happens with, the Moore's law, yes?
Haven't we reached a limit with Moore's law, though?
They say it's slowing down, all right. But that's where this is going, which is that, how small can you make a tiny little chunk of silicon? Well, if we go away from silicon and we use individual molecules themselves, I'm not sure what would be smaller than molecules. But that's the general thought, is that we can use, let's use muons or something, to conduct electricity. But if we take polymers and align them, and a single polymer chain serves as an electronic component, then of course Moore's law advances. That's the general thought. So they are definitely working in this area, trying to figure out how to use molecules or small groups of molecules as semiconductors or conductors. Okay, and that's always nice because things can be smaller as a result. We'll talk about this, electrical displays, and of course rechargeable batteries and solid electrolytes. We're trying to get away from lead acid batteries still. We still use them, but a lot of things are going in the direction of these polymer-based batteries that have a lot of advantages, and of course the excitement is we can figure out how to have a 500-mile range on your electric vehicle. That kind of thing, if we can just cram more charge carrying capacity into the batteries that they use. Any questions about that? So only one person knows what Moore's law is. Now everyone knows what Moore's law is. Right? Electronics get smaller. Yes?
I was just giving a thumbs up.
Okay, all right. Okay. So, light-emitting polymers, and yet in the service of electroluminescence conductive polymers. And I'm holding one of those in my hand. So this is an OLED screen. Came on the technological scene around 2012, all right, and has taken over since then, because we can take what used to be large and heavy and make it relatively small and very portable, because we have a thin film that does the work of what we used to have. And actually, let me talk about that very briefly. So, what is this? About 50 years ago, in South Columbus, they used to have a plant that made cathode ray tubes. Has anyone ever seen a cathode ray tube? All right, so some people have. Okay, so those are the old TVs. All right, maybe that sounds familiar. And the thing about the old TVs, and this is, I'll just expand on this sketch a little bit, is we used to have a phosphor screen, all right, and we would use electronic field to drive photons or electrons, depending on what the technology was, toward that phosphor screen. And when they would hit that phosphor screen, it would glow. All right, this is still used in other applications. That's a great thing about phosphor screens. And this also had to be under a high vacuum. And we had various electronic connections in and out of the backside of these things. And the key thing for purposes of discussion is that it was made of glass. The whole thing was made of glass. And thick glass, too. These were tremendously heavy. So the TV that I can tuck under my arm at Best Buy and walk out with would require 3 people to carry the cathode ray tube version of that, because there's so much glass, heavy glass, built into these things. And then they're a vacuum as well, which complicates the manufacturing process. Does anyone ever hear one of these things break? It makes a sucking sound when you break them. Oh, you have heard? Okay, cool. All right, so I'm not the only delinquent then. So that was difficult. That at South Columbus they made, I don't know, millions of these things before they shut that down. And one of the reasons is why is this technology came along and killed off the cathode ray tube. And so what this technology consists of is there is a thin layer of glass, but very, very thin. And the anode in this context is indium tin oxide, which is a certain ceramic material. Maybe you know why ITO is useful? You never have enough? And again, you're just materials people. You don't know anything about electronics, apparently, I've been told. Okay. All right, so ITO is great because it allows for electrons to move, but it's also transparent. Right? You can see right through it. So ITO is called ITO glass is what they call it. So it's great stuff. So this serves as the anode, and then on the other side, we have the cathode, which is just aluminum. All right, very pure aluminum in a thin film form. So everything here is very, very, very thin. And then in between all of that, we have our conjugated polymer, the stuff we've been talking about here. And so this arrangement, and we'll talk about exactly what goes on here, this arrangement allows for light to be produced by the conjugated polymer layer. And I'll talk about how that's done in just a second. But first I'm going to show you this little movie, if I can. So you can go look this up in Nature. So this is 1990 they came out with this. So, about 20 years later they finally made something out of it. But this is just showing you that back in the early 1990s, they were exploring this, and they could cause this process, this combination in a thin film to emit light. And this is the very crude initial demonstration of that, and we're a lot further along, obviously, than they were back then. And so, how does this process work? We have polymers that can emit light when excited by the flow of an electric current in conjugated polymers. That's essentially what's going on. And it involves a lot more detail than that. And so we know we have these polymers, and they have an ability to conduct electric charge. They're not copper, all right? You're not going to power a toaster with them. But we know they can allow for electrons to move. Not a lot of them, but in this case it's enough. And so what we're doing is we start out with a cathode. Aluminum by far. I'm not sure why you'd want to work calcium or magnesium, but because they also burst into flame pretty easily. And this serves as a source of electrons. And so what they do is they inject these electrons into this light-emitting polymer layer, as it's called. But it really is just a conjugated polymer, the stuff we've been talking about, conjugated polymer with double bonds in it. And so these electrons don't go very far. They just kind of sit there at the interface between the cathode and the polymer layer. And on the other side, we have the ITO anode. And that anode is putting holes into the polymer layer.
You have to go to a lot of trouble to make a polymer conductive.
What?
Yeah.
Not that much trouble. I mean, compared to other things. The question is make it useful. That's the hard part. It's not making it's not that hard. And so what happens is these holes are injected in, and they do all the work in terms of motion. So they find a polymer chain, they latch onto it, and they start moving along those double bonds. And eventually they go to the other side and they encounter this layer of electrons. And what happens is they establish what's called an exciton, or an electron-hole pair. So that's what this is. And as you can see, kind of, sort of, it's the electron orbiting around the hole. All right. And so this is not a long-term state of matter, but it is something that sets up. But ultimately what happens is they crash together. So it's like matter, antimatter. They come in contact with each other and they eliminate each other. And when they do that, right there at that interface, they crank out light. And so that's what you saw in that little video a minute ago, is the emission of that kind of greenish light coming out of the polymer layer when it's put into this kind of sandwich. All right? And of course that's coming through the ITO because that's transparent. Any questions about that? So it's kind of like, I don't know, ESCA or XPS. You guys aren't familiar with that probably, but anyway, so there are other things in physics that use the same type of process. Yes?
I almost a dumb question. Does this do like the different colors, or is it just only like white?
We'll get to that. Yeah. The answer is yes, with some modifications. Yeah. All right, and so we apply the electric field, causes the injection of positive charges or holes in this context. The majority charge carriers, meaning that they travel. They don't. That's what that means. The ejections of electrons, and usually the minority charge carriers, meaning they don't travel very far. It goes into the polymer film from the two electrode contacts, formation of electron-positive charge pair, that exciton within the polymer, which eventually, and when I say eventually, it's it's femtoseconds, but it does form a stable pair. But eventually that annihilates and gives off that little bit of energy in a packet of light called a photon. All right, and so that's the basis for this. And the question becomes, what's important? How do we get to different colors? So these light-emitting polymers are conjugated polymers. Light emission efficiency can be tuned by using different polymers. And so, let's see, where is it? Polyaniline was kind of one of the first ones that people did a lot of work on. There were some people here in physics who were sort of associated with the New Zealand group, and they did a bunch of work in polyaniline. But unfortunately, polyaniline is kind of a not a very weak light, and polyacetylene, as it says down here at the bottom, is even worse than polyaniline. But we have other materials. Let's see, polyprol is a good one. Polyparaphenylene is another good one. Those are giving us much brighter lights than what you saw in that little video. All right, and so they have different efficiencies in terms of how many excitons can be formed and maintained and then annihilated. All right, and that's what boils down to the efficiency of light emission from these thin films. And so the more of the conjugation they have, the more the intense the emitted light, because you can get more holes and electrons into that same polymer layer. All right, and so this ability to conduct electrons, as crappy as it is for polymers, there's a big race to come up with the best polymer to make that happen. So we also, getting into the color issue, conjugated polymers emission color and emission efficiency can be fine-tuned by manipulation of the chemical structures. So it's not just a matter of how much light they give off, but what wavelength the exciton gives off when it's annihilated. Question?
Are trans and cis polyacetylene both really weak, or is one better?
They're both about equally weak. Yeah, that's a good question, but neither one of them is all that great. So we have, in this context, this choice of different structures. So now you can see it's starting to get pretty far away from polyacetylene, the simple polyacetylene structures. But it turns out that it is pretty important. So we see in these different materials, we see sulfur, we see lots of double bonds, especially double bonds within these ring-like structures, these 5-carbon rings. Well, it's 4 plus sulfur. And we also see that for these different structures, we get, well, let's switch colors. We get red, we can get green in one case, and we can get blue with these other cases. And so what that means, hopefully you're thinking of RGB, all right? RGB, red, green, blue, gives us the ability to blend colors and make whatever the heck we want in terms of the emissions from these systems, okay? So if I put, let's see, if I put, is it red and green together, I get yellow, okay? And that's one way of doing this. And so that's certainly an aspect of it, but let's talk more about what you might go into Best Buy and see. So what they do is they take these things and they stack them together. So they'll have a little unit of red, a little unit of green, and then a little unit of blue, all right? And by themselves, what this does, when you put them together and turn them all on, activate them, and so there's a lot of electronics, a lot of circuitry, obviously, controlling these individual layers, what you'll get out of it is the most boring thing you can get, which is just white. All right, and so that's not particularly useful, but what they do is, and I have to draw the darn thing again. So we have green. I'm sticking with the order because that is significant. What we can do is have multiples of these things. And we can put a green filter, just call it green filter, so a thin film of polymer that has a green emission, and then we can put a red filter, again, very, very thin polymer films, and we can put a blue filter. All right, everyone see that? And so these stacks are doing what they do, which is crank out white light. All right, 3 different polymers, put them together to give white light, and so these white lights are being fed into these filters. So every one of these units, if you go into Best Buy, is an element. So when they talk about 4K TVs or whatever what is the latest one? 4K. Anyway, they always talk about how many elements there are on a screen. All right, some people get really excited about how many elements. I personally don't see them. But anyway, so the more elements you have, the more lifelike things. How many football players can you see in great detail is determined by how many elements there are on a TV. So each one of these is an element. Okay. And what you do is you can operate these independently of each other. All right, so if I have all 3 of these things sitting next to each other, and if I operate them all at the same time, I'll get white light. All right, if I come over here and I turn off the blue one, I'll get yellow light. All right, or if I take the blue one and I run it at 50% of its normal output, then I'll get something in between white light and something else. All right, you'll get a lighter yellow or something like that. Does that make any sense? And so this is how these screens work. That's how they give us these colors, is because the electronics are telling these things to operate independently in certain defined ways to give color. Yes?
So when let's say it turns on red, would it only be the red filter, like the red section and the red filter that's turned on?
Exactly. So if we have a Buckeye on the screen, all right, and we want it red, all right, the scarlet, so what they'll do is they'll turn off the green and the blue, and the red operates on its own. Now, of course, as we all know, what is red? It's garnet, it's scarlet, it's all kinds of things. So there's a lot of tweaking going on to get to the exact color of red it's supposed to be. All right, and so there's a lot of very, very fast logic going on in these systems to give us exactly the right color of red. Yes?
Would the red section and the green and blue filter also be on? Or would it be only the red section under the red filter?
Oh, I see what you're saying. No, that's an important point. So, this is kind of the underlying unit, the white light. All right, and so and this is kind of part of tuning the red color. You operate all three of these, you get white light, you put them behind a filter, and you get whatever color that filter gives you. All right, and you can independently tweak these three things to change the color of red. That's really a lot of what goes on here. All right, so as you might imagine, it's really sophisticated electronics that control all these things. Really tiny, really thin electronics that make all this happen, that give us these screens, that get us away from the enormously heavy CRTs that we used to have to deal with. Any other questions? So again, you go into Best Buy, and you'll see these everywhere. You're surrounded by OLED screens. And that's what they look like. Thousands of red, green, and blue OLEDs next to one another and switch them on and off independently. And then within an element, we control the characteristics of emitted light to change the color that we want to see. And they work like pixels in a conventional LCD screen, so we can produce complex, high-resolution colored images for a variety of applications. Some a lot less important than others. I don't really care how fast my shaver is going, thank you very little. But this is sort of giving you the general idea of what's happening. It's a very thin film, and we can get, in this case, green colors, and then the next second we get red color, and the next second after that we get blue colors. And so, as you can see, it's very thin, all right, and that still gives us the colors that we're looking for without having to work with these really large, high vacuum glass materials. Okay, any questions about all that? So if you want to review the previous lecture on conductive polymers, that's probably not a bad idea. All right, before the final, just to make sure you're clear on some things. Okay, some of the homeworks and concept tests are here. And then, as I said, on Monday, we'll have a review session, kind of extended review session, and then no class on Wednesday. Anything else? All right, you guys have a good weekend.